Everyone, this is Logic Coding. So this question is called Jump Game 3. I'm actually going to make a series of 1 and 2 because they're such classical, dynamic, and greedy algorithms. But today, let's just focus on the third one. So we're given an array of non-negative integers array, and we're initially positioned at a random index given as start index of the array. And when we are at any index, we can jump to the right, I plus array I, or to the left, I minus array I. And I want to return true if we can return to any index with a value 0. So if we array I equal to 0, then we can just return true. Notice we cannot jump outside of the array. If I is smaller than 0 or is equal or greater than array.size, then it's not valid. We just return false. Cool. So for this problem, we actually can do both DFS and BFS. I'm going to write both. So as you can, according to the solution, it's kind of like a path. So we kind of thought a graph traversal. For both DFS and BFS, we will be visiting each element at most exactly once, so the time complexity will be O(n), and the space complexity for both will also be O(n), since we need to allocate a Boolean. We need to allocate some indicator for each array. Actually, for DFS, it is possible to optimize it to be O(1). Okay, so with that said, let's now implement DFS first. So let's see. We just use recursion. So the ending condition is, so if I is out of bounds, smaller than 0, or I is start. If start is smaller than 0, or start is greater or equal than array.size, then we know it's false. If array start is already equal to 0, then we just return true. Otherwise, we go forward. We go one step forward. Array start plus array, or can reach array start minus array start. If we just run the code, it can pass for this case. But for this one, it actually have stack overflow, which means it will always be always. So let's look at what this happens. So at the beginning, it starts with this 2. So it can move to here, or it can move to here. So if move to here, then it goes back, and then it continues to move back and forth, so it's stuck. So what we can do is we can mark it. So whenever it's visited, we just change, since this is passed by reference, start equal to negative -1 times array start. If the size is smaller than 0, we also return false, which means it has already been visited. Now let's try to submit. Cool. So DFS, it works, and as I mentioned, there's a BFS way to deal with this problem. Now let's comment this out and try BFS. The idea of BFS is at each node, we look at its right and we look at its left, and we have a visited Boolean array to mark. So let's set the BFS up. So we have a q as an int, at the end, we just push our start to the queue. And while, let's set the BFS up, while my queue is not equal to empty, oops. Let's first get the size. And for each one at the current level, we do q dot front, q dot pop, and if I need a visited boolean, const int n equals to array.size. If it's not visited, then I visit it. So how should I visit it? First, if my array current equals to 0, I just return true. If not, and if it's not visited, at the end, I should mark it as visited. Somewhere in between, if it's not visited, then we should consider both its neighbors. So we have left equals to current plus minus, and we have its right array current. When it's within bounds, we should push it. Within bounds means when left is greater than or equals to 0 and left is smaller than greater or equals than 0 and left is smaller than n. The same thing for the right. Yeah, I think that's pretty much it. This is for the BFS. Let's try run the code and then submit it. Cool. So for this kind of problem, I think the most important thing is to realize that we need to treat the solution space as a graph, and we want to start with the start index, and we want to find in this path, either by DFS or BFS, there exists such a node that equals to 0. And each edge is given by the length of the array. But other than that, I think it's important to know the recursion thinking as well as the DFS and BFS templates. But that's it for the jump third one. And I'm going to upload the first one, which will use dynamic programming, and the other one use greedy algorithm. They're all very classical problems, so stay tuned. See you next time.